Look at your hands. Look at the room around you, the earth beneath your feet, and the stars overhead. According to the strict mathematical laws that govern our reality, none of this should be here. You and everything you have ever interacted with are statistical anomalies. To understand why, we must look back to the first 3 seconds after the Big Bang. The universe was infinitely hot and dense, filled with high-energy photons constantly colliding. Those collisions spontaneously produced pairs of particles, one made of regular matter and one made of its exact opposite, antimatter. Because they were created in identical pairs, the universe had an equal amount of both. And when matter and antimatter meet, they annihilate each other completely, turning back into pure light. When we measure the cosmic microwave background, the leftover radiation from the early universe, we can calculate exactly how many photons were produced by that massive annihilation event. That calculation tells us there were originally around $10, $89 pairs of particles, but if we count the ordinary matter surviving in the observable universe today, we only find about $10, $80 particles. That means the annihilation was incredibly efficient, but imperfect. For every billion pairs that destroyed each other, one single matter particle survived. All the galaxies, planets, and oceans we see today are built from those lucky remnants. If the mathematical laws governing reality were perfectly mirrored, nothing would have survived. There has to be a flaw in the math. We've known about this mathematical mirror since the late 1920s, thanks to a physicist named Paul Dirac. When Dirac wrote down an equation to describe the electron at rest, he found it had 2 valid solutions, one for positive energy and a strange one for negative energy. Instead of throwing out the strange result, he proposed that this negative energy represented an entirely new, undiscovered type of particle. He predicted a perfect mirror image to the electron. Today, we call it a positron. According to quantum field theory, a positron has the exact same mass and the exact same spin as a normal electron. The only difference is that it carries an opposite charge. Because they are exact opposites, they can perfectly overlap in space. When an electron and a positron meet, their opposing charges cancel each other out, the physical excitations in the quantum field disappear, and 100% of their combined mass is converted into pure energy, radiating away as photons. This principle applies to almost all subatomic particles. The mathematical equations demand a perfect twin. Yet, if nature insists on a perfect balance, we wouldn't be here to observe it. Since our universe is overwhelmingly filled with matter, there must be a physical crack in this mathematical mirror. For decades, physicists relied on 3 absolute symmetries to describe the universe. Charge symmetry meant positive and negative interactions behaved the same. Time symmetry meant particle collisions looked identical whether playing forwards or backwards. And parity symmetry meant the universe had no preference for left or right. Combined, these form CPT symmetry, a core mathematical assumption holding together our entire understanding of special relativity. Assuming nature is perfectly balanced is one thing, but proving it is another. In 1956, an experimental physicist named Chien-Shiung Wu, often called Madame Wu, decided to actually test parity symmetry. She cancelled her holiday plans, went straight into the lab, and began a highly complex experiment. She aligned the nuclear spins of radioactive cobalt, 60 atoms, in a strong magnetic field and tracked the direction of their electrons as they decayed. If the universe truly had no preference for left or right, the electrons should have fired off equally in both directions. Instead, she found that 60% of the electrons moved exactly opposite to the nuclear spin. The universe inherently favored a left-handed direction. When other physicists heard the results, many flatly refused to believe them. Nobel laureates demanded she run the tests again. There had never been a hint in all of physics that the universe cared whether an experiment was reflected in a mirror, but independent labs quickly reproduced her work, confirming the data. Parity symmetry was broken. And if one supposedly absolute rule of nature can shatter, the others might have microscopic fractures too. Finding a crack in the combined CPT symmetry using antimatter is now our best hope for explaining why the universe contains anything at all. To find that crack, physicists have to create the universe's most volatile substance. Here at CERN's antimatter factory, protons are accelerated to 99.93% the speed of light. They are then smashed into a dense iridium target. The impact is so violent it pushes the strong nuclear force past its breaking point, forcing a chaotic shower of new particles, including antiprotons, into existence. These antiprotons burst out of the target, traveling at 96% the speed of light. Much too fast to study, they are fed into a deceleration ring called ELENA, which uses powerful magnetic lenses to steer and focus the beam, eventually slowing the particles down to a creeping 1.5% of the speed of light. But you can't just put antimatter in a jar. If an antiproton touches the wall of any normal container, it instantly annihilates. The solution is a penning trap. This device uses a ring of superconducting magnets and electric fields to suspend the antiprotons in the center of a tube. The entire trap is then cooled to -269 degrees Celsius, creating a frozen vacuum comparable to deep space. Safely isolated in this extreme cold, teams running the base experiment can finally get to work. Their goal is to measure the magnetic moment of the antiproton with staggering accuracy, checking to see if it is truly the exact equal and opposite of a normal proton's magnetic moment. Preventing this substance from touching our physical reality is an engineering marvel, and it is designed entirely for one purpose: to stare at a trapped antiparticle and wait to see if it disobeys the rules of our universe. While the base experiment looks at magnetism, two other experiments, G-bar and AlphaGa, are probing an even deeper mystery. They want to know how antimatter interacts with gravity. Specifically, if you drop a piece of antimatter, does it fall down or does it fall up? You can't just drop a charged particle because even tiny stray electric fields will overpower the force of gravity. You need an electrically neutral anti-atom, and making one requires antiprotons and positrons. To get the positrons, physicists fire a beam of near-light-speed electrons into a tungsten target. The deceleration rips electron-positron pairs out of the vacuum, but it also releases intense, deadly gamma radiation. Once they've extracted the positrons and guided them safely through heavy shielding, they carefully merge them with the antiprotons. If the timing is exact, the negative antiproton and the positive positron lock together into an atom of antihydrogen. Because their opposite charges balance out, the resulting anti-atom is perfectly neutral and immune to electric fields. Even then, the anti-atom is jittering with too much thermal energy. To get a perfectly accurate gravity measurement, the G-bar team aims to freeze the anti-atom down to 10 microkelvin, just a tiny fraction of a degree above absolute zero. Only when it is perfectly still can they turn off the magnetic trap and watch it fall 20 centimeters. Physicists are constructing multi-million-dollar accelerators, working behind massive blocks of radiation shielding, and inventing entirely new ways to reach absolute zero just to watch a single atom drop a few inches. The sheer scale of this effort proves how desperate the search for asymmetry has become. Every time an anti-atom is dropped or an antiproton's magnetic moment is measured, the physics community holds its breath. If the alpha-G, or base experiments, detect even a microscopic part per billion difference between the behavior of matter and antimatter, CPT symmetry breaks, and if CPT symmetry breaks, the foundational equations of modern physics break with it. The standard model of particle physics and Einstein's theory of special relativity are built on the mathematical assumption that this combined symmetry is absolute. A single discrepancy will force us to rewrite a century of science. To date, the mirror remains perfectly intact. Every measurement has shown matter and antimatter behaving exactly as expected. To find smaller and smaller discrepancies, CERN has portable traps that can sustain a vacuum so perfect they hold antimatter isolated for hundreds of days, allowing it to be driven on a truck to even more precise facilities around the world. We are pushing our engineering to the absolute limit, intentionally trying to break our most successful, well-tested theories of physics. We are doing it because breaking those theories is the only way to earn the ultimate prize, discovering the mathematical error that allowed us to exist. With all this talk of annihilations and shattered laws of physics, it's easy to look at antimatter as a sci-fi super weapon. Pop culture certainly treats it that way, like the plot in Angels and Demons, where terrorists steal a fraction of a gram from CERN to blow up Vatican City. But the math of actual production brings us firmly back to reality. Antimatter is incredibly difficult to accumulate. If CERN took all the antiprotons they produced in a year and annihilated them at once, it would only generate enough energy to heat a drop of water by a single degree. To make just 1 gram of antimatter, the factory would have to run continuously for longer than the age of the universe. We don't have enough antimatter to destroy a city, but we do have enough of it sitting in our own kitchens. Ordinary items that contain radioactive isotopes, like a bunch of bananas, are constantly producing trace amounts of positrons as they naturally decay. You don't even need to eat a banana to find it. The trace radioactive elements inside the human body mean that the average person generates around 180 positrons every single hour. There is no need to fear an antimatter explosion in a secret lab. The substance physicists are so desperately trying to trap and study is sparking into existence inside your own body right now. You are a 1 in a billion anomaly, actively producing the very mystery we need to solve to understand our own existence.